Hello, students, and welcome. Today, we are going to look at a very important topic in organic chemistry, the classification of amines.
Okay, let's dive straight in with a curious puzzle. Have you ever wondered about this? We have tripmethylamine, which is heavier, but its boiling point is lower than the lighter dimethylamine. It seems counterintuitive, doesn't it? Normally, we expect heavier molecules to have higher boiling points. Well, the answer lies in one very simple idea. And that simple idea is classification. Understanding this one concept is the absolute key. It helps us predict an amine's reactivity, its basicity, its solubility, pretty much all of its chemical and physical properties. So let's start with the core idea. It's a simple rule based on counting, really. It's as easy as 1, 2, 3.
At this simplest level, we have what is called a primary amine, which we write as 1 degree. In a primary amine, the nitrogen atom is bonded to just one carbon-containing group. And please notice, it has 2 hydrogens attached to the nitrogen.
Next up is the secondary amine, or 2 degree. Here, the nitrogen atom is bonded to 2 carbon groups. This leaves it with only 1 hydrogen attached to the nitrogen. And finally, we have the tertiary amine, or 3 degree. In this case, the nitrogen atom is bonded to 3 carbon groups, and this is important. It means there are no hydrogens directly attached to the nitrogen at all.
Now, this is a very common point of confusion for students, so let's be very clear. Do not mix this up with how we classify alcohols. For amines, the rule is simple. We count the number of carbon groups attached directly to the nitrogen atom. For alcohols, remember, we look at the type of carbon the OH group is attached to. This is a critical difference, so make sure you have it clear in your mind.
To make this concept unforgettable, let's use a very simple analogy that I think will help you remember this for life. Just imagine a primary aim as a one-legged stool. It's quite wobbly, isn't it? It needs extra support, and it gets this support by forming hydrogen bonds with its neighbors. A secondary aim is like a more stable two-legged stool. And a tertiary aim? Well, that's like a stable three-legged stool. It is self-sufficient and doesn't need that external support from hydrogen bonding. But why does this simple counting system even exist? Why do we bother classifying them in this way? What problem does it actually solve for us as chemists?
This concept exists because it gives us a powerful tool to organize and, more importantly, to predict the behavior of amines. Without classifying them, we wouldn't be able to explain why their properties and reactivities are so different. Classification brings a beautiful order to the whole topic.
Now, let's build a clear mental image that you can actually use in your exam. This will help make the concept very concrete in your mind.
Okay, picture 3 pyramids, and at the very top of each pyramid is a nitrogen atom. For a primary amine, the base of the pyramid has 1 dark sphere, that's our carbon group, and 2 small white spheres, which are the hydrogens. For a secondary amine, the base now has 2 dark spheres and only 1 white sphere. And finally, for the tertiary amine, all 3 points at the base are occupied by dark spheres, the carbon groups, and notice, there are no white spheres left. The key difference is the number of hydrogens available for bonding.
Now, let's come back to the puzzle we started with. This chart explains everything perfectly. The primary and secondary amines have NH bonds. This allows them to form strong intermolecular hydrogen bonds, which require more energy to break. That's why they have higher boiling points. But look at the tertiary amine, trimethylamine. It has no NH bonds, so it cannot form these strong hydrogen bonds. And that is why its boiling point is so much lower, even though it is the heavier molecule. The puzzle is solved. And please remember, this concept is not just some theory for your exams. It has very important real-world technological applications. For example, in water treatment technology, anion exchange resins are often made using tertiary amines. Now, why tertiary specifically? Well, because they don't have those NH bonds, they're less likely to form strong hydrogen bonds with the water molecules around them. This actually improves their ability to interact with and capture pollutants and other anions, which helps make the water cleaner. You see? The classification directly impacts the function.
So, to recap everything, what are the most important things that you really need to remember for your exam to master this topic? There are just 3 things. First, the core idea. Simply count the number of carbon groups attached directly to the nitrogen atom. 1, 2, or 3. Second, the mental image. Remember that 3-legged stool. More legs mean it's more stable by itself, but it has less ability to form hydrogen bonds. And third, the example. Recall the boiling point puzzle. It's the perfect proof of why this matters. It's all about the presence or absence of those NH bonds.
If you can just hold on to that core rule, the simple stool analogy,
and that one key example, I promise you this entire topic amines will feel much, much lighter and far easier to understand, both in your studies and in the exam hall. Keep revising, and you will do wonderfully.